All right, what we want to do is we want to talk about gases, their properties, and how those properties are important. Now, chances are you already know a lot of this stuff, so we'll talk a little bit more about why they're important and what that means for us. So to talk about properties of gases, I want to say that, for example, the particles are very far away from each other. And one of the things that means, or one of the results of that, or maybe the other way around, that's because each particle sort of uses up more space than the particle itself actually occupies. So if you think about a person, say me, I only require this much space, but if I start flapping my arms, if I start moving around, then I'm going to need more space, otherwise I'm going to be bumping into people. Gases are kind of like that. Each particle itself has a whole lot of room to move around before it runs into another particle. And you see in this picture where we would often draw solid, liquid, gases in this way, we'd pack the solids all nice and tight in some sort of nice orderly arrangement. Liquids are packed not quite as tight, but pretty close, but there's no real order to them. And then gases are all over the place and lots of gaps in between. And that also then means that gases are going to take the shape and the volume of the container. And I want to emphasize the volume of the container for a moment. If there was only one particle of gas in that container, it would occupy the entire volume. Not all at once, but it would occupy the entire volume. If I put 1 liter of gas into a 100-liter room, that gas now occupies 100 liters, I should say. So gases always take the shape and the volume of the container. And the volume of the container is sometimes something that is going to cause us the most trouble getting our heads around. Gases are also compressible. Now, part of it is because you have this very large gap in between those particles. Compressing them just means I'm squeezing taking away some of that squeezing them closer together and getting rid of some of that large space in between them. And gases are a fluid, they flow, and we notice that in the weather, that wind that we feel, that's just gases flowing. But I can also show that with this, and I would have loved to have shown it for real, but the best I can do right now is this. And what we have in this little clip is somebody is doing the vinegar and baking soda reaction, and they're holding their hand over top of the reaction vessel, it's a measuring cup, trapping some of the carbon dioxide gas that's in there. And then what they're going to do should be right around now, is they're going to slowly lift their hand off it so they don't disturb the gas too much, and then they're going to pick up that measuring cup and they're going to pour out the gas. And we know we're pouring out the gas because we can see the candle being extinguished. Now we want to move on to some other aspects of gases rather than just their properties. One of the aspects is pressure, and we're going to have to talk about pressure and understand pressure and use pressure all the time. Pressure, by the definition, is the amount of force over a given area. If you were in physics, you spent more time on this. We're not going to spend that kind of time, and that's okay. But for us, I want you to understand that pressure is always a push force. Pressure always goes from high pressure to low pressure, never the other way around. So if you're trying to drink a milkshake and you're really sucking on the straw, it's not that you are sucking the milkshake up the straw. What's happening is you are creating a low pressure, and then high pressure around is actually pushing that milkshake up the straw. Not hugely important, and you don't have to go around correcting people who are drinking milkshakes or instructing them on this, but pressure is always a push. For us, the only thing we're going to be using is the metric units of pressure, and those are going to be kilopascals. However, day-to-day use, if you're inflating tires, for example, you're probably more familiar with pounds per square inch, which are PSI. Now, when we talk about pressure, there's two kinds of pressure that are important, and we sometimes have to distinguish between them. One is a closed system, and a closed system is inside a container, the lid is on. So an aerosol can or something like that. And then the thing that causes pressure is the particles inside that container pushing against the sides of the container. So if you pump up a tire, right, gas is not coming out, but the pressure is caused by the gas pushing the air, pushing against the tire, which is how you see the tire actually inflate and able to hold up a car. That is just air pressure holding up that car. An open system, container is open, the lid is off, gases can come in and come out. That is actually caused by the weight of the atmosphere. So if you pay attention to weather reports, they'll talk about high pressure systems, low pressure systems, and things like that. And really what's happening there is it is the weight of the atmosphere. So as different air masses move around, they're going to exert more or less pressure on us. So in the first picture, we have the particles colliding with the sides of the container. Now you can imagine if those particles started to collide with the side of the container a lot, they could actually burst through the sides of the container, and that's something that happens once in a while. And then in something in here where the open system, we still talk about pressure, but then it's the weight of the atmosphere. Now you might think that that can't be very much, but it actually is quite a bit. You have roughly 1 ton of air on top of you, but because it's a fluid, you can move through it fairly easily without really experiencing the full weight of that all the time. Plus, we're kind of used to it. But atmospheric pressure can actually be pretty significant. So in this little clip, what we have is a person who's heating up a pop can on a thing, and it's an open pop can, so gases inside are able to expand and escape. And then when they put it in the water, it cools quite quickly, but air can't get back in, and the can ends up being crushed. That crushing action on the can, as rapid as it was just the atmospheric pressure pushing in on it. I have another one here where there's these half ball, that is supposed to be muted, this half ball thing where they're vacuuming out, so they're taking all the gas out of there, and then they close off a valve so no gas can come back in, replace it with a handle. And then what they're going to do, once they have the handle attached, and it takes a little longer to attach the handle than what I would like, once the handle's attached, then they're going to pull on it. So you have air outside those spheres pushing in, but there's no air inside. So they cannot separate those spheres. Now what happens is now he's opening the little valve, air can come back in, and it comes apart quite easily. That is just atmospheric pressure. Okay? Anytime you use a suction cup, anytime you use they can get these things for lifting glass, where they put or I've seen for if you're sticking something to your windshield, like a GPS or something like that, you've got that little vacuum, that little suction cup with a lever on it. All it's doing is something like that. You're taking the gas, the air out of there, and then atmospheric pressure is holding it on. You also have gases inside marshmallows. So marshmallows, big foamy, squishy things. So what we have is gas trapped in there. Now in this clip, what's happening is they're going to vacuum out the air around the marshmallows. So now right now you have air outside pushing in the marshmallow, air inside pushing out. But if we take the air pushing on the marshmallow, take that away, the marshmallow gases inside start to push out more and they expand. So now all the marshmallows start to look bigger. Right near the end here, some of that air inside the marshmallow starts to escape all by itself, where it says he just popped. So some of the air inside the marshmallow has escaped the marshmallow. Now what we're going to do is we're going to let the atmosphere back in. So now we're going to have more push on the marshmallows, and you'll find that they squish down much more than they did before because of the air that's escaped. We're going to talk about temperature, which is not nearly as interesting to me as the pressure is, but there is a bit of a problem, a bit of an issue with temperature, and that is we cannot use the Celsius or the Fahrenheit scale. Even though I will always tell you a temperature in Celsius, you can never use that temperature in Celsius. And the reason for that is, when we're doing calculations, negative numbers and zero numbers that are possible on both scales will really mess up our stuff. So we have to use what's called the absolute scale, sometimes called the Kelvin scale. So the nice thing is that there's a really simple conversion. It's a little inconvenient, I suppose, in that it's 273, but whatever number I have in Celsius, I just add 273, and that gets my temperature in Kelvin. And 0 Celsius is the temperature at which ice melts or water freezes into ice, which is just sort of kind of an arbitrary thing. You could have anything you want. 0 Kelvin is the point at which, the temperature at which all particle motion stops. It is the lowest possible temperature. There are no negative Kelvin temperatures. So that's something that we're going to have to get used to and remember. Okay, next time we're going to talk about gas laws, which is doing math with gases. So we're going to have temperatures and pressures and volumes, and we're going to do some calculations with them. Talk to you then.